Alright, so in this lecture we're looking at movement of ants, how the ants moving and why they're going on a one line, right? So, and can we simulate something like this? Well, let's talk about this. It is kind of interesting factor that you may have seen uh, when the ants are moving, they're walking on the same line, right? So they setting up a path and they're moving on that, one after the other. They're not going as bunches, they're just going following one after the other. Why it happens, right? So usually the ants are moving on a one line due to the chemical that they produce or spreading by the one who's moving on the front. That chemical is called pheromone. So each ant will leave a path uh, by dropping those pheromone chemicals, so the others can follow. Right. So that is the communication actually uh, they having on to set up a movement like that. Okay. So how do we simulate something like this? Right. So um, we employ empirical observation of the ants when they are leaving the pheromone. What is empirical observation means? Like, for example, we remember that we did empirical models, right? So what is empirical model we did? So we get the graph like this, and then you have some data falling in certain close enough certain areas, and then you get one average path that follows to the close enough. So that is what the idea of empirical model. So this is empirical observation is. Here ant is not perfectly going behind the other, so it might be somewhere close enough, so you can actually see there will be a certain path and the ant is moving close by. So that is the empirical observation means in this case. Okay, right. And so before we move on, obviously this is about ants, so we have to set up some assumptions. uh, Usually when you observe the behavior of ants, we can come up with certain observations, I mean the assumptions on this, to simplify something, uh, the movement of ants, right? Right, so let me see what are the assumptions here. So suppose that these ants are containing a square area. Of course we're going to model this, so we're going to put ants in a square area. So that means obviously we will have some sort of a square like this. Maybe we will put it in a glass container, and so we can set a boundary for the ant. So that's what the idea here. Ants does not turn completely in one time step. So the if the ant is like this, right, he so this is his head, let's say, right, and we are not consider ant would turn completely, like for example turning backward like this, right? So that is not going to happen in one time step. Either left or right they will turn, but not all the way back, right? So this is what does not turn around means. So it says turn around, so that means moving from one side to the other all the way. Tends to move towards the unoccupied neighborhood location with the greatest amount of chemical. So we going to grid this like this. So these are the cells that identify the location of the ant. So if the ant is here, the next turn of the ant will be the highest number of pheromones. So either this one, either this one, either this one, whatever it is, how much chemical it has. If this one has more chemicals, so the ant is going to move towards that way. So that's what it means. Okay. So if no such movements available, assume the ant is waiting in its location. So if there's no pheromone or available, that means uh, if there's an ant here, he's not going to go there, right? So he will wait. uh, so that's isolation, or the idle part take place. And employ an avoidance on the waiting strategy prevent collision. So that means if I have one here, right, and if you have another here that has no clue to go this way or this way or this way, so he's waiting, that means this one also waiting, so he's not going to go and hit him, right? So there's no collision in between. So that's what avoidance or waiting strategy means. Okay, right. And then with movement of from a site that has certain threshold chemicals, so that means one of these sites or the cells, the ant deposit additional pheromone for reinforcement. So what that means is if the ant goes here, yeah, the amount of chemicals in this shell or the site will increase. So that's what it is. So by the time it's decay, the amount of chemicals you have, but if there's the ant moving, it becomes stronger, right? And this is what the decay part means. It diffuses and also dissipates. So that means, yeah, it's going down. It's not going to stay there forever. So the time is the factor that it's taking off by the time, right? And the start with a straight line, right? Straight trail, increasing amount of pheromone, perhaps laid by ants heading for food. So that means, yeah, so we assume there's a line, right? That, and this line is pheromone. So the ants will assume they already set up a path for others to follow, right? We do not consider the food or the nest. So there's no nest here, no food here. Just assume that there's a path actually with the chemicals. So in that case, see how these ants should move towards that. So that's what the idea here that we're gonna follow, right? Right. So saying that, so let's move on to determine the variables. So we have a closed container as we said before. So the closed container is the walls that we have. So we call it border, right? So we have some sort of a border, right? So it says in the ant grid, each element of the first and the last row of a column has a constant value. So what does that means is the first and last row. So this is the first row, this is the last row, all right? So each element of the first and last row has a constant value. So that means we set up some values here, right? And we set some value here as well. So we'll look at what are these values are. So we say 1 2 3 4 5 6 whatever it is, right? And the border, right? And then also this one is talking about columns as well. So this one and this one. So what does this means? I set up a border. In this case I put number 6 on this, all of it, right? So that means that's my border and it's not going to cross that border, right? So all these are 6, right? Okay, so then I'm setting up empty cells as zeros. So whatever the empty here, I set it as 0. Okay, and a cell with an ant contains a constant, right? So a cell with an ant, if there's an ant here in any of these, so for example, if you have this kind of a structure, right? If the ant is here, I mean this is what I'm looking at from the center, and if there's an ant here, right, or here, okay, or here, if I have it here, I put 1 there. if I have it in the south, I put 3 there, right? The west and east, so these two will values like that, right? So this will be east, so in that case this is 2 and the west is actually 4, right? And those are the values putting there. And if the ant is staying here, so the weighting is 5, surrounding is, we said, set up as 6, right? So that is something that you just put some values in there, right, in order to determine what's going to happen at the beginning. So why are we putting numbers here? Well, the good part in putting numbers is we can generate numbers by random integers, right? So the random means you just call rand function, and this rand function can have some limit, maybe mod 7, right? So it will generate 0 to 6 values, right? But one rule is this whole border is already 6, so I don't want to put another 6 here and here. So in that case you can have 5 or 6 here, so it will produce 0 to 5, and you anyway going to set up your border as 6. Okay, so this part I can generate by the random number. Okay, so this is what here they are also saying the random integers 1 2 3 4 and 1 2 3 4 are representing the directions north east west, and respectively we will have 1 2 3 4 in these values they're talking about here, right? I think this is a typo right here. It has to be and or whatever. Okay, I think it's or. This double means it's or here. Okay. Right. Anyway, so these we assign the random integers and then represent the directions. Okay, and then we just throwing it wildly. So that's what we starting with. So let's look at an algorithm and see what we can do. So before I go to the algorithm, let me talk about this a little. Okay, and here is empty means ground containing no ants. So ant about to move or just move to the north, either from the north, we just put 1, right? Ant move about to move or just move from east, we put 2, and so on. And then the border is 6. So this is exactly what I was talking about earlier, right? And then we had to talk about pheromone as well. We set up a border value, the boundary as 0.01 minus, so we'll come to this in a minute. The ant is moved to the neighboring available cell with the maximum amount of pheromone. Okay, so this is the chemical that is in there, because we are employing absorbing boundary conditions, right, in the pheromone grid. So okay, so now there's an issue that we have to consider here. So the one issue is, of course, if we have boundary, we put it as 6, as I said, but there's little factor we can put here, prevent this ant is moving to the boundary. Is one reason that we can prevent this is set this boundary to negative 0.01 pheromone, right? So that means it's a very little pheromone amount around the border. That means ant is never going to go there. So if there are pheromone here, of course they will move towards that, but never is going to be at the edge, right? So this is a good way of controlling the ant. As I said, the boundary to negative 0.1, thus the ant will never tempted to step out from the grid, so it will be always inside the container because of this reason, right? So when you simulate, it's the best way of doing that. Okay, so that's one of the best ways of doing that. Okay, so then initialize most of the interior cells as zeros. That means what? Well, it is empty, no ants in there, right? However, for the pheromone trail, in the middle of the grid, we will have a horizontal line. So this is where I'm going to model this. Well, that means we're going to have in our grid, we're going to have something like this. If I draw the square, this is my grid, and we will have a horizontal line here, which is we consider as pheromone. Right, so this the value of pheromone on this one is very strong. So it has an increasing pheromone value. So it will start from a little and go a little bit high on this side, right? So okay, so this means so we'll have increasing amount on that. So the set the maximum pheromone, so we call it max pher. So how are we going to set up this? That's the next question, right? How are we really going to have a gradually increasing amount of pheromone in this line? So this is what they're talking here, right? How are we going to set that up? So how are we going to set that up is set the maximum pheromone. So we consider I as the column, right? And n is the maximum number of columns. And then we set up the pheromone amount as maximum is 50. So in this case, if I have something like this, right? And if I have the pheromone amount or the chemicals amount in sort of order, like this one is, let's say, first column, this is second column, this is third column, and fourth and fifth, right? So let's say like that, okay? And maximum number of columns we have already is 5. And each counter means 1, 2, 3, 4, 5. So this one I will put amount of pheromone is 1 over 5 multiplied by the max amount, right? So that is the amount I'm putting here. So that means 1/5 of the max amount will be there, right? On the second one, I will have 2/5 of the max. So that will be a little bit more than this one, right? And the third one will have a third amount for 3 over 5 amount of multiplying by max. So this will be greater than this, right? So this will be like this. I mean other way around. So this will be like this. This will be like this, right? Okay, 1/5. The 2/5 is greater than that. 3/5 is more greater than that. So when you go like that at the end here, so you have 5 divided by 5 multiplied by max. What does that means? Well, when you come into that, well, this to this cancel out. That means the last column or the place here will have the maximum number of chemicals. So it will be increasing in certain order. So like this. Right, so that is the amount that you're putting in each one. So it will be increasing at the end. Why? Well, if you assume there are food nearby, so most of the ants will be closer to this area than they're moving from their home or whatever it is, right? So in that case, we consider this one has less, this one has more, right? So that's the purpose or the reason that we're setting it up with this equation. So that helps it to increase from a low value to the high value, right? Okay, so that's the idea of setting up the chemicals on it, right? So then let's look at more the rules. So these rules are going to apply for our algorithm. Okay, so what are the rules? So let's analyze a little bit about rules here. So the rules, there are two, we're breaking into two because I'm writing three functions in order to simulate this. So rules of the function sense. So we have function called sense, which points towards its new location. So we will have some rules here. Um, Empty cell does not point towards the direction. So there's an empty cell means there's no direction. He can go anywhere, right? He can go this way. He can go this way. So this way. This is not no point out on this one, right? And does not turn to a cell which the creature just came. So they are not turning back. So that means if they come here, they are not going backward. So they will go either one direction like that, right? And does not turn to a location that is a border site. So if I am in the border like this, and if this is an ant, he's never going to face this direction. So there's a border here, right? So that is this right here. And then ant does not turn the location, turn to a location that currently contains an ant. So if there's an ant here, he's never going to face this way or go there, right? So you have two choices to move actually, right? So that's what it is. And otherwise an ant turns in the direction of the neighboring available, right? So it is not occupied, and if it is not a border, if it is only available, so that means if this one is 0 and if this one is 0, and this is what ants is planning to move on. But if there's no pheromone on this, maybe he's not going to move at all, right? So you have to have the greatest amount of chemical out of these two in order to this one to move, get to move on these ones, right? So that is another rule, right? And then if no neighboring cells is available, ant will not move. So that means if we will wait here if there are ants around you, right? Or if it is a border here, and then if you have ants around it, well, he will wait. So those are the rules for sensing, right? So this is what the sensing rules. So there are more that we are looking at here when it comes to the walking part. So these are the rules. So you can see the numbers here. We're going to apply those numbers with the rules, these rules in our algorithm. So you can see much, you can get a good idea on it. Okay. So now the cell that remains empty, if there's a cell which remains empty, the amount of chemical determines by the constant amount, of course, and it will dissipate for sure. So the evaporate does not fall below 0. So obviously if there's no chemical, it will be set to 0, right? Why is it not go below 0? Because the boundary is anyway going to be the boundary here is negative 0.01. So if this goes beyond that, well, it doesn't make any sense, right? So the boundary is the lowest. In that case, they are not going to move out of the border, right? Okay, so this is always the case that you have to follow. And an ant facing in a certain direction will move into the neighboring cell. So that means if he's facing this way, obviously he's planning to go there, right? So that's what it is, right? And as long as no other ants are occupied, so he will move. Otherwise the ant will stay in the current cell. Of course we talk about that in the sense already. If an ant leaves the cell that has pheromone above the certain threshold, right? So we consider something called threshold, which is a range actually. So that amount of chemical increases by the set amount. So that means okay, so what that means is if you're really in one cell, right? So if there is one cell, that means the pheromone amount in that cell is going to be increased by some amount. so it will be a little bit stronger than before, uh, because of the chemicals will produce by this ant will live in that cell. So you have to increase the chemical amount, right? Okay, and then if the ant stay in a cell, the amount of chemical remains the same. So that means if he's waiting here, you don't increase it. But when you move out, you increase this one by amount. Okay, so that's what it is, right? Okay, so that means leaves the cell. So whenever the ant is leaving the cell, you put some amount. If ant stays in the cell, so we talked about that already. So that's this. And then after moving to a new location, the ant faces toward the cell from which the ant came from. So that means if I'm facing this way, right? If my facing this way, and if I move here, right, now my ant is facing actually the same direction. He's not going to turn this way or this way unless there are more chemicals make him move, right? Right, so that is that. And all right, so let's look at more, uh, and we come into the algorithms, right? And movement for one time step consists of two actions, right? So there are two actions for each time stamp, sensing and walking. So there are two functions I'm going to write, for one for the sensing, the other one for walking. And sets the empty neighboring site and turn to one which is the greatest chemical. That's already, we know that. And if possible, to do so without colliding with another ant, so that means there are no ants on the neighboring site, the ant moves towards the preferred location. So only the movement happens is if there are no ants occupied the cell, right? After the reaction, sensing walking with 8 neighbors of a site. So what is 8 neighbors? And what is the neighborhood style for 8 neighbors? Right. That is, we talk about that in fire. We talk about that in diffusion. So that's called, if it is 8, it's Moore's neighborhood policy. If it is 4, it is von Neumann's, right? So anyway, so let's look at this. So this is the site, and we have a bunch of variables here. So we look at each of these, and the function to return the direction, which is ant is turning northeast, southwest, or stay, right? So those are the 5 conditions, right? So the 5 conditions are there. And should ant planning to remain, and its current location is called stay, of course, and then or you just moving. Right, so what are the inputs? The site, we have the site, NA, EA, SA, and WA. North ant, east ant, south ant, and the west ant. So all these, north, east, south, west. So those are things which is right here. Okay, so then if a cell contains an ant, right, then it is value represent the direction from which the ant came in the last time step. So that means what? If the cell contains an ant, it will be value represents the direction from which. So that means we put 1 or 2 or 3 or 4. The cell, we count it by where the ant came from, right? So that is, so if we come from north, we just set the cell as 1. So that's what it means. Okay, so if you're not clear of it, so let's say this is the case. I have this, and then the ant was here the last time. So what is the last time is t minus delta t. At that time ant was there, right? So this is south, right? Okay, so that means at t time, on when this one happens, this cell take the number 3, right? So that's what here. So now this cell is number 3. Why? Because the last ant moved from here to here, right? So that's what it is. Okay, so that's what meaning by that rule, or the assumption on this. I mean the inputs on this, right? And well, the value represents a direction from that, so that's what we talk about. Okay, so then the pre is the integer the input. So the input is a grid, right? And apply sense extended in the in a timestamp. So that those are the two things that you're gonna apply. So in the first input on this walk uh, algorithm, right? So we have here the Fermat grid is the corresponding Fermat, right? So that is what we call Fer grid. And then here we have the ant grid, right? So where the ants are. So what you're going to return here is the grid actually. So how those are behaving. So it says n number of rows and columns in ant Fermat grid is -2. So that means if there are n number of columns and rows, right? So that means n by n square. In ant or Fermat grid is -2. That means you just subtract or initialize this to -2. I mean, we initialize everything by subtracting 2, right? So that is not going beyond 0 actually. So the new ant grid will be the ant grid. So that means the new Fer grid will be the Fer grid. So what are these two things? Let me talk about that for a minute. So you will have, in this case, we're going to maintain two things. One is what we're going to maintain our grid with full of ants in there, right? So these ants actually produce the chemicals, right? So that means I have to have another grid, and in this one we get some values like 10. So if there are no if the ant live here, by the time this amount will reduce to 8, so that is -2 each time. So that's what we're talking about here. So it will reduce some values. If there another ant comes here, obviously you have to increase the value. Okay, so anyway, we have to maintain two grids. So one is for ant, one is for the Fermat amount that you have. And there are two for loops here, which is you can travel through each cell. So in this one, the for going through each internal row index, do the following. I think I will leave, the rest is the algorithm actually. I don't want to push you to that much. This is actually more easy for the computer science people to understand, but the rest I'm not going to test you deep on this algorithm. This will stick with the rules actually. So if you know the rules, those are the rules we are applying here in each step of this algorithm. So if you feel interested, just go through the algorithm. It's nothing but the rules that we have up there, and we apply each of them. Okay, and okay, so then one more thing that interesting part here is we have another parameter we're introducing here called the probability of ant. If there a probability of ant in there, I mean the probability of ant exists. So that's what it means. So this function is the third one, which is called ants, and then this function returns a list of ants and the Fermat grids in the simulation of ants movements. So yeah, we have this the simulation going with all three functions together. So here again, what is the input for this function is nothing but n grid, right? So that is one thing, and the probability of ant is a probability that the ant initially occupied the cell or not. So that's the other thing. And the diffusion rate is, the amount of pheromone dissipate or reduce. And we have a timestamp. Okay, so so the timestamp will be, you mark it down each step. So what you're going to return from this function is initially subsequent ant grids of each time step, and that is what we call simulation actually, right? Yeah, so this is nothing but calling all the functions up there. So there are two functions we calling initialization and the list of it, and then make it happen, right? So once you do this, this is what the interesting outcome on this kind of simulation. So this is the initial setup. You can see we set up the pheromone, right? The chemicals on this line right here, and then the ants are all over. And by the time, so what they do is these ants are moving towards this pheromone, right? So you can see the entry point right here, and then it's nicely rising in order. So you can see after some t times, you can see most of them are coming towards this middle line, right? And the end of this, at the end of this, you can see more of these ants. Very few are there. He has no choice of going anywhere because there's no pheromone around. So that can be a glitch also, right? But most of them are going on a line. So you can see now the ants start marching on a line right here, right? So this is after 11 grid time. This you can see now these are just gathering together. So this is the idea actually. How we put this, we put bunch of rules, and then we set up a bunch of assignments, and then we came up with the nice simulation. So this is what this kind of a complex situation, so we can address in a minimum knowledge we have about ants, right? I mean, we really don't know actually pheromone is enough for ants to talk. Are they I mean communicate? Are they really talking? We don't know that, right? So would they have some sensors on their brain, or the vibration they're picking up from one to the other, or the sensors telling them something like communicate by mind? Who never knows, right? So we cannot test those throughout the ant. So anyway, according to our assumption, we believe it is only pheromone is the thing that ants can communicate. They don't scream or yell, right? So in that case, this is what the simulation gives you. So what are the things you should know on this? Well, yeah, the algorithms just have a brief idea, which is not that I'm not going to make it hard for you, right? But the things that you should learn on this is how when you go into a model something in this complex, the assumptions make it more easy for you, right? So we have a bunch of assumptions here, right? So make sure you understand the assumptions, and then the values of the initial setup. So there are a few of them right here. We have that, and then yeah, how you set up the maxfer, right? And then the rules. So those are the rules that are very important, and all the others are algorithms actually. So just have a brief idea of algorithms. You don't have to go through them thoroughly. But have a general idea what we're doing here. Okay, so because this is related to more coding, so that's why I'm not going to go through that. That is not one part of you. So mostly it is interest the computer science students than anything else. All right, so saying that, so I will
conclude this lecture, and so we complete the semester with all the lectures we planning to do. Only good luck with the finals, and then make sure everybody's turning in a good report. Okay, all right, okay.